Our assignment was about the integral, which can be seen here. So for the first part, we were supposed to sketch the domain of integration. We can see that the x has the bounds 0 to 1, which is the area which we pointed at. And y has the bound 0 to the square root 1 minus x squared, so we can conclude that the area in the xy plane is a quarter circle with the formula x squared plus y squared is equal to 1. Then the lower bound of the z is square root x squared plus y squared, which will form a cone, the red one here, with the formula z squared is x squared plus y squared, and the upper bound is square root 2 minus x squared minus y squared, which is the green sphere here, with the formula x squared plus y squared plus z squared equals 2. The domain of integration is the black marked part with the lower bound the cone and the upper bound the sphere in the z direction, and it cannot exceed the quarter circle on the xy plane. Then the second assignment was to write the domain of integration in spherical coordinates. So the spherical coordinates are rho, phi, and theta, which are respectively the distance to the origin, the angle with the positive z-axis, the angle with the positive x-axis. So for the distance of the origin, the smallest distance is the bottom tip of the cone, which is 0, and the biggest distance is the top as the sphere, which is square root 2. So the bounds of rho are 0 to square root 2. Then for phi, the angle to the positive z-axis, the smallest angle is at the top of the sphere, which is 0. The largest angle is within the cone, which is 45 degrees, so 1 over 4 times pi. Then for theta, which is the angle to the positive x-axis, which can be seen, the smallest is 0, where the x-coordinate is 1, and the largest angle is where y is 1, so that is 90 degrees. So it goes from 0 to a half pi. Then the third part of the assignment was to compute the integral. As you can see, the integral with the Cartesian coordinates is far too difficult to be able to compute. So we transformed it into an integral with spherical coordinates. We got the following formula: rho squared times sine squared phi times cosine theta times sine theta. And then we got the Jacobian, which is rho squared times sine phi. The formula we got because x is equal to rho sine theta sine phi cosine theta, and y is equal to rho sine theta sine phi, and z is equal to rho times cosine phi. After we got that, we made it so that the Jacobian and the formula were 1. So you get rho to the power 4 times sine to the power 3 phi times cosine theta times sine theta. Then, because it's kind of difficult to compute the cosine sine theta, we made it into an easier form, so a half sine 2 phi theta. Then the second part, sine to the power 3 phi, is also quite difficult unless substitution is used. But we chose a different method, so we rewrote it, and it becomes minus 1 over 4 times sine 3 phi plus 3 over 4 sine phi. The rho part was not changed because that's easy to compute. Then the first integral, this can be seen here. The second one here with the bounds, and the third part here. If we fill in the bounds, we get the following. So 1 over 4 plus 1 over 4 times minus 1 over 24 times square root 2 minus 3 over 8 times square root 2 plus 1 over 12 minus 3 over 4, and then times 4 over 5 times square root 2. And then we change this a little bit because we add the terms in between the second brackets. And we get this minus 5 over 12 times square root 2 minus 2 over 3. And then we write it like this: 2 over 5 times square root 2 times what's in the brackets. And then we get the following: minus 1 over 3 minus 4 over 15 times square root 2. And because we were computing a volume, because we had an integral, it should be the absolute value of the solution.